Thank you for introduction. And also I found there is a type of synchronization. Synchro, yeah. There is no O here. Sorry. Oh. So I just changed the subtitle is Mathematics Driven by Biology. Okay, I heard that this morning, yesterday, Professor Huang said conference driven by research, something like that. Research driven by conference. so I changed this subtitle, Mathematics Driven by Biology. So here is a brief outline of my talk. So first I'll remind you what I mean by synchronization. And then I'll talk about two main models for synchronization. And then briefly talk about what I'm going to do in this lecture. And then I'll talk about some dynamics of so-called Cramoto oscillators and then Loewe oscillators. And then I'm going to tell you what I'm doing now. Okay, so this is now is 2 o'clock, just right after lunch, so it's a nap time. So to wake up I'll show you one story that I learned from Taiwan last November. Okay, so I just read. Okay, one day in class, the teacher assigned his students to write a composition, "If I am a manager." All the students began to write except a boy. The teacher went to him, asked the reason. Okay, think about it. What this boy answered. Thomas, do you have idea?
Sure. I let my people write the story.
Okay, it's close. But okay, what about our dear chairman? Okay, so I'm waiting for my secretary. Okay, so we are waiting for our secretary. Okay, so let me start with synchronization. Synchronization basically means adjustment of rhythms of some oscillatory system due to their weak interaction. So I'll show you two videos that I downloaded from YouTube. The left video is about this flashing of neurons. I don't know if it's real neurons, but I downloaded from the YouTube. The right video is about the beating of pacemaker cell. Your heart is kind of made of pacemaker cell. So okay, why it doesn't work? Anyway,
This one is working.
yeah, it's one working. So it's a heart beating due to the synchronization of pacemaker cells. So in mathematical literature, there are two types of modeling to model this phenomena. One is based on so-called pulse coupled one model. That means you consider action potential. If action potential reaches certain critical threshold, then the neurons or this oscillatory thing fire. So you fire and then down. So you integrate fire model, for example. The other one is called the phase coupled model. So in this talk, I'll just focus on phase coupled model because it's easier than the pulse coupled one mathematically at the moment. Okay. Okay, what happened? Oops. Okay, so I'll tell you two main characters. So the first one is so-called the Stewart-Landau oscillators. So let's consider we have a network, all-to-all network. So every nodes are connected to each other. So at each node, let's imagine we have some oscillator. Whose state is denoted by g sub I, which is a complex valued function at time t. So the dynamics of Stewart-Landau oscillator is governed by this differential equation, complex, So K is called coupling strength, and is the number of Stewart-Landau oscillators. So suppose we don't have a coupling, say K equal to 0, then you have this single equation. So each equation, each zi are decoupled each other. And so in that case, if you use this polar coordinate, because zi is complex valued function, so you can use a polar coordinate, then you can decouple this equation for the amplitude and the phase. So it turns out the phase velocity, so-called frequency, is given by this omega I, so-called the natural frequency. And also if you look at this amplitude equation, certainly you see that Ri equal to 0 or Ri equal to 1 are equilibrium. And also if you do the phase, it's this simple case, a phase diagram, you see that Ri equal to 0 is unstable, Ri equal to 1 is stable. So in dynamical system language, so-called the unit circle is a limit cycle for this decoupled system. Okay. Now you turn on the coupling, and if coupling is too strong, then every oscillator are dead. So, but if coupling strength is in the certain range, then you can, if you do numeric simulation, I didn't show here, but if you do numeric simulation, the solution of this guy approach to some limit cycle, like a circle. The radius not necessarily equal to 1, but some radius. So we are interested in these limit cycle oscillators. Okay, so I take ansatz zeta j to be this one. Okay, because already we assume that this limit cycle is the unit circle, and then focus on the dynamics of this phase. So if you plug these ansatz into these equations and compare the imaginary part, then you'll get to this so-called the Kuramoto model. So the frequency is the sum of natural frequency plus the frequency variation due to the coupling, phase coupling. So if coupling is 0, then the frequency is determined by natural frequency, so no synchronization, no collective behavior. But if you increase K compared to this natural frequency, then due to this nonlinear coupling, some collective phenomena emerge. So this model in synchronization literature is one of the prototype phase model. Okay, now let me switch to quantum network. In the previous case, we have a classical network. So we have a network, and each classical oscillator sit in the node. Now let's assume that we have a quantum network. So at each node, we have a quantum system is sitting there. Okay, electrons, whatever. And these electrons, this quantum system interact through some laser. Okay, let's imagine. Okay, at the moment I don't see any real quantum network at the moment, but let's imagine at the moment. So then in 2009, the Australian physicist Max Lohe proposed the following matrix valued ODE system. So UI is a d by d unitary matrix. HI is d by d Hermitian matrix. Okay, so it's a matrix valued ODE system. HI is this Hamiltonian, is constant Hamiltonian in this case. K again is coupling strength, and the coupling through this quadratic thing. It looks weird, but this one, okay. Anyway, it's proposed by physicists. So if you don't like this model, complain to him. Okay, but why this Lohe model is interesting? In the special case, so for example, one dimension, say t equals 1. So you have a 1 by 1 unitary matrix means what? It's the complex number with the modulus 1. Okay? So you can rewrite ui to be like this, polar coordinate. Hi is a 1 by 1 Hermitian matrix, means it's a real number. All right. So if you put this ansatz into this Rohe model, then exactly what you get is a Kuramoto model. Okay. So Rohe model is one of the extension of the Kuramoto model. So that's why in Rohe paper he used the non-abelian Kuramoto model. Okay, non-abelian because it's a matrix algebra. Matrix group is non-abelian, as we know, except t equals 1. Okay. Another extreme case is if you turn off the coupling strength k equal to 0. K equal to 0, so we don't have this. I told you ui is a unitary matrix, so if you multiply unitary matrix ui to the right hand side, then ui dagger ui. By the way, ui dagger is ui star Hermitian conjugate. Okay, because I just adopt the physicist notation. Yeah. So then what you get? Exactly the Schrödinger equation in finite dimensional form. Okay, so you have this explicit solution. So somehow this Rohe model is a extension of Kuramoto and Schrödinger equation. Okay, that's why I call the quantum Kuramoto model. Okay, so now, I already told you our main characters. Now, so the goal of this talk, I'm going to show you some emergent dynamics of these two models and some related models. Okay, in particular is Kuramoto model and the Rohe model. Okay. Okay, so first let me tell you the Kuramoto oscillators. So suppose we have 50 Kuramoto oscillators. Initial data is randomly chosen from 0 to 2 pi on the circle, okay, randomly. This natural frequency is withdrawn from this unit interval, uniform distribution. Okay. And we take coupling strength to be 0.8, okay? So with this choice, I just numerically integrate this Kuramoto system. Then, okay, so nothing happened. Not interesting phenomena happened. Okay. Now, I take the same initial data, same natural frequency. I just increased coupling strength from 0.8 to 2.2. Okay. And we simulate, then what you see, some train-like phenomena. Physicists call the emergence of entrainment state. So you see this, if you do numeric simulation for genetic initial data, you as long as coupling strength is large enough compared to this guy, you see this phenomena all the time. So the numeric simulations suggest that this state, so-called the phase-locked state, I'm going to give you the rigorous definition later, but this phenomena, this train-like phenomena, emerge from generic initial configuration as long as coupling strength is large enough. Okay, so this is what physicists believe. Yeah. Of course, never physicists try to prove this. Okay. However, okay, so here this is the definition of phase-locked state. So as you've seen from previous numeric simulation, Kuramoto model in general do not have equilibrium solution. Okay, but if you move with the average natural frequency speed, then you have an equilibrium. So it's called the relative equilibrium. It's like our embodied system in Newton equations do not have equilibrium in general. But if you move with this rotating frame, you have an equilibrium. called relative equilibrium. So likewise, Kuramoto model do not have equilibrium in general, but it has a relative equilibrium. Relative equilibrium is called the phase-locked state. So in other words, this guy is a phase-locked state, means by definition, the phase difference, transversal phase difference, is a time invariant. Okay, so I call the phase-locked state. Okay. So here is the problem that I'm interested in, so-called the complete synchronization problem. So as I show you before in the video simulation, for given genetic initial configuration, for sufficient large coupling strengths, we want to show that phase velocity, the difference of phase velocity, tends to 0 asymptotically. Okay? So, of course, we have to make sure what I mean by genetic, what I mean by sufficient large coupling, how large it should be. Okay? So I have to specify these two things in the mathematical theorem. There were some earlier works on this problem by starting from the engineers in control theory. These three people in 2004, they somehow formulate these things in some identical oscillator case. That means all natural frequencies are the same. And they used some LaSalle invariance principle from dynamical system. But I didn't find the mistake, but this paper claimed that there is some mistake here. So in 2009, these two engineers again, what they prove is as long as coupling strength is large enough, if initial phase diameter is less than this guy, pi over 2 minus epsilon, then they prove this. Okay, and this engineer and together with my former students, we extended this result to the half circle. Okay, pi. Okay, so as long as initial configuration is confined in the half circle, we could prove this complete synchronization for k larger than d of omega, d of omega. Okay, here what I mean by d of omega is the diameter in the natural frequencies, omega I minus omega j. Okay, so and years later, two Chinese mathematicians, Dong and Xu, they show that for all initial configuration and for positive coupling strengths, this complete synchronization emerges for identical oscillators. Okay, so the natural question is, what about non-identical oscillators? Okay, so when I heard this result from my former postdoc, I didn't believe. So I told my former postdoc, who was students of She, there must be some mistake. But it turns out no mistake. So because I got stuck in this special class, but they showed that they proved for all initial configuration. So that was surprised me a lot. So then what's the main difficulty with the previous approach? Okay, so previous approach for non-identical oscillators confined in the half circle setting, this phase diameter does play the role of the Lyapunov function. Okay, so I use the kind of Lyapunov approach, function approach, using this diameter of phase as a Lyapunov function. And all the technical estimate, we need this assumption. Okay, so because of this choice, we had to restrict our initial data confined in the half circle. Okay, that was the mathematical difficulty. So and so, maybe a couple of years struggle, we realized Well, just forget about diameter and go back to order parameters. So you have this is just configuration of phase. That means on the circle, on the unit circle. Okay, so you have n rotors basically. Then, if you consider the centroid of these n rotors, oscillators, so as long as this guy is not zero, the magnitude and this common phase are well defined. Okay, and also you can see that this is a convex set. Therefore, R, the centroid is in somewhere inside the disk. So this order parameter R is always bounded, basically 0 and 1. If R is close to 1, that means all phases are confined in the same phase, so-called completely synchronized state. R equals 0 means due to some cancellation, symmetry, okay, if rotors are located a symmetrical way, then R equals 0. So somehow R measures the synchronizability of the whole oscillator system. It's called the order parameter. And 2011, with Marshall-Slemrod, we studied the dynamics of this order parameter R and phi in finite dimensional setting for different purpose. At that time, we were interested in slow, fast dynamical system approach for Kramoto model. So at that time, we used these dynamics of order parameters in this way. And then around 2013, together with this Dr. Hwa-Gil Kim from KAIST now, and my student Jin-Young Park, we realized if initial data has a positive order parameter, that means initial state is not a phase-locked state, and the deviation from the common phase is smaller than this guy. Remember, if this is happened, then initial phase diameter is slightly greater than pi. Okay, because all right. So then we can show that in finite time, the configuration evolved to half circle. The once configuration evolved to half circle, then we can apply previous theorem. So if you, for example, this configuration, the diameter is larger than pi, so we can apply previous sufficient condition theorem, but we can show that in finite time, this configuration evolved to some configuration confined in half circle. Okay. But again, this show you this restriction can be bypassed by using dynamics of order parameters instead of phase diameter. So this is psychologically is an important step because I got stuck this phase diameter half circle for a while. Now this is not essential. Okay, so once you know something is not essential, then if you work hard, then you can get theorem. So this is the result by the Hwa-Gil Kim and Yu Sang-woo in Seoul National University. So if initial data satisfy this condition, okay, that means initially it's not a phase-locked state. This is a technical assumption, but it can be deleted. Okay, so initially phases are different, and then what you can show is that there exists large coupling strength K infinity, which is computable, may not be optimal, but it's computable, so that your configuration evolved to some phase-locked state in L infinity asymptotically. Okay, so this is the theorem that we are looking for. Of course, there's still a lot of room for improvement because this coupling strength is not optimal. You can relax some, some conditions. So, but let me just show you the just key idea briefly. Okay, so first the Kramoto, if you use this least scale time and natural frequency by k, then you just divide by k here and using different time scale. So remember, we are interested in large coupling strength regime. K is large compared to this guy. So that means you fix k, that means now you are in the small coupling strength, okay, because k is large. So first, so now we fix the coupling strength 1. We look at the small natural frequency regime, okay. Okay, so let me give you just ingredients for the proof. The first ingredient is that the Kuramoto model is a gradient flow with an analytic potential. The Kuramoto model can be written as a gradient flow like this. The potential is analytic function. But the only difficulty is that now Kuramoto, the right-hand side is certainly is 2 pi periodic function in theta, right? So you can think this as a dynamical system on a torus, okay? However, now we are extending this. If you have dynamical system on torus, then you can embed in the Euclidean space. So now I'm looking at this Kuramoto model as a dynamical system on Rn, okay? So theta may not be bounded, okay? So this potential is not bounded because you have this linear term. But this term certainly bounded, but you have a linear term, so this potential may not be bounded below, okay? The second thing is, so now we just consider a fluctuation from the average motion, because Kuramoto model has some conserved quantity, average is conserved, kind of. So therefore, we just look at the fluctuation from the average motion. So this theorem tells you, as long as your fluctuation is bounded, then you have a convergence. Okay? So no chaotic motion. Okay? This is a little surprising, because this is the n is larger than or equal to 3. Bounded solution doesn't guarantee the convergence. But this Kuramoto model, because of the gradient flow with the analytic potential, just boundedness implies convergence. And also for identical case, omega I equal to 0, what you can show that is except one oscillator, every oscillator aggregate to the common oscillators. Okay, so for this initial data, eventually, if you all oscillator is aggregate to common average, common phase, except at most one. Okay, so that's the key idea. And then you can compare with the identical and non-identical case, because by scaling we are considering the small omega I, so it's close to the identical case. So you can estimate this difference between non-identical identical thing. So the last key step that we need, so we need to prove the fluctuations are bounded. Then gradient flow structure tells you convergence. So you need to prove boundedness. So I call the formation of a chain of black holes. You have a chain of absorbing regions. Once the oscillator get in, they cannot get out. Okay, so what this lemma, technical lemma, tells you, more than half, as long as coupling strength is larger than certain number, which is complicated, but what you can show that this diameter of phase is bounded, uniformly bounded. So it's a little technical thing. So let me just skip. So basically, we use the structure of the equation crucially, okay, instead of just using the Lyapunov thing. Okay, now after that, to refinement of the previous result, the first so-called what we can prove also is the asymptotic phase locking if and only if finite collisions. So convergence to the relaxation to the phase-locked state, the collision between oscillators is at most finite. So they are equivalent. So in previous 2012, as long as this initial data is confined in half circle, we show that there are at most finite collision. But this observation is actually genetically true. Okay. The second finite result is that you can ask, so somehow the size of the relative equilibria, how many relative equilibria exist? Okay. This is natural question. So what is the cardinality of the set of all phase-locked state? But unfortunately, there's some simple example. For identical oscillators case, if you choose mu to be any number between 0 to 2 pi, the number of oscillators is greater than 4. If you set this one, then you can check this is a phase-locked state with the order parameter equals 0. So if you simply naively ask this question, it's a continuum, okay? Okay. So we have a continuum of phase-locked state for the Kuramoto model, even for identical oscillators. So to get a finite result, we need to restrict phase-locked state to be the order parameter to be positive. Okay. Then you can define these questions. So how many phase-locked states exist with a positive Kuramoto order parameter? It turns out it's a finite. For identical case, basically all phase-locked state with a positive order parameter is basically permutation of these guys, 0 or pi. So it's either synchronized state or bipolar state are possible phase-locked state. So you can measure the size exactly. And for non-identical case, we don't have an exact number, but we can have an upper bound, at least 2 to the n. N is the number of oscillators, okay? I still don't know whether, probably it's close to here, but the methodology doesn't tell you exact number. Okay, so let me switch to the second topic. Again, we consider this quantum network. Of course, this question, this quantum synchronization is not my question. You can, in the Kimball from Caltech, he's the physicist from Caltech. He wrote a paper on so-called quantum internet in Nature. He said, can we make all quantum states at each node synchronized through some dynamic process? Okay. Of course, he didn't write any model. He just, I don't know, maybe he, frankly speaking, I didn't understand his paper. So, but so again, we have this Lohe model, matrix valued model. So before I told you t equals 1, it reduced to Kuramoto, k equals 0, it reduced to the Schrödinger equation. Now if it equals 2, you have a 2 by 2 unitary matrix, 2 by 2 Hermitian matrix. Then we can use we can use the Pauli matrix as a basis of 2 by 2 unitary matrix group. So you can expand UI as a linear combination of Pauli matrices here. And then look at this coefficient. It turns out this coefficient and phase satisfy this coupled system. Certainly you see some trace of Kuramoto here. So here one of the audience, Sono Choi, we did lots of work for this coupled system in last several years. I don't know how many papers we wrote. A lot, I think, right? Because at the time we only can do t equals 2. Okay. Now I tell you the general thing. So now I don't restrict to t equals 2, t equals 1. Okay. Any d. So So we have a Rohe model. It turns out this Rohe model has two invariants that we know. One is this quadratic quantity invariant. Okay, it's a conserved quantity. It's integral. And also, this model is invariant under right multiplication by unitary matrix. That means what? UI is the solution. You multiply, you consider this quantity, which is the UI times the another unitary matrix. It turns out UI satisfies the same equation, but you change the initial data. So it has a translation invariance somehow. This is reasonable because Kuramoto case is a rotation invariance, right? Because it's the dynamics on the circle. But we have to define what I mean by phase-locked state. Now, our main object is a matrix, okay? So, UI is the phase-locked state means UI, UJ dagger is constant for all I and J. Okay, so what that means, if you use d equals 1, UI is e to the minus I zeta I. You can write this explicit one. This turns out this guy, in special case, corresponds to e to the minus I zeta I minus zeta j. So this constant means zeta I minus zeta j is constant. So special case, it reduced to the known case, okay? So, and then Rohe flow achieves asymptotic phase locking means asymptotically t goes infinity, this quantity approach to some constant. That means it has a limit, okay? So, and the phase locked state is basically, you can characterize phase locked state to be unitary matrix times matrix exponential. Lambda plays the role of phase. So lambda satisfied UI amplitude satisfied this algebraic constraint. Okay. So our main strategy is to use the Lyapunov function approach. I know this may not give you optimal result like Kuramoto case, but at the moment this is what we can do. Okay. We use this diameter. Here norm is called the Frobenius norm. In the matrix group, you have a Frobenius norm means A is a matrix. It's A, dagger A. You take a trace, take a square root. It's called Frobenius norm. This is common in quantum mechanics. So we use this norm, this as a Lyapunov functional, and we derive Grunwald inequality for this Lyapunov functional stuff. If you calculate carelessly, or just rough calculation, then you don't see this good term here. Then you cannot get this exponential, Grunwald type good inequality. So in order to get this good term, you have to be careful. Okay. So this is the result. I think just published in Journal of Statistical Physics. So coupling strength is larger than, this H, D of H, larger than this number. U naught is the alpha ball. This norm is the Frobenius norm. Then what you can show that asymptotically phase locking achieved. And then this convergence is exponential and some sort of the uniqueness. So this special n equals t equals 2, these things was already observed by joint work with this Sono Choi here. Okay, so let me tell you what I'm doing now. It's quite natural. If you have this n oscillatory system, okay, and quantum oscillatory system, you might ask, what if n goes to infinity? So we have a large number of quantum coupled system. Then, of course, technically to solve this coupled big system is too costly, okay? So you want to approximate this large system by simple equation. So you can ask this mean field limit n goes to infinity. Okay, so this is the ongoing work with the functional course. So I wrote down kinetic theory meets algebra. So again, our phase space is this guy called unitary Lie group times the Lie algebra, associated Lie algebra. So I had to look at the algebra book again after 98. After I passed the qualifying exam, I thought I never study algebra again, but I have to be back. Okay, so f is the density function on this phase space, now group manifold, and you can using BBGKY hierarchy, you can write down the kinetic like a Blasov type equation on this group manifold. Okay, and you can prove the convergence from this one particle distribution function to this empirical the marginal distribution function. Distance is measured by this Wasserstein 2 distance, so-called the Monge-Kantorovich distance. The convergence is laid here. Okay, so okay, now because Lohe model, we assume that all quantum states are finite. Okay, so you can naturally ask, what about you have infinite quantum state? So that means you have a Schrödinger equation, a free Schrödinger equation coupled with some nonlinear term. It's so-called the Schrödinger-Lohe model, was proposed by Lohe in second paper. Originally, Dr. Sono Choi wrote down this, and then we found that the same, almost the same model is in the paper. So again, we used this Lyapunov function approach. Our Lyapunov function is the L2 distance between these two wave functions. Okay, it's a L2 distance in space, and so for example, for identical oscillator case, that means this potential, one body potential are the same. Okay, so every quantum particles is under the same one body potential, external potential. And positive coupling strength under some restriction on initial data, because this restriction is due to this Riccati type differential inequality for this diameter. Then you can prove this exponential convergence. Of course, how to relax this constraint? I don't believe this is optimal. This is not optimal because maybe from some generic initial data, we must have this. And the basic estimate depends on this Corona type equation. For non-identical case, identical case, that means this guy equal to 0. So you can use the Riccati equation. If this is not 0, then this estimate, this differential inequality only give you upper bound. Okay, it doesn't give you lower bound. So what you can do, so-called the practical synchronization. If coupling strength is large enough, if initial data is restricted in this sense, then this guy, upper bound max, like a limit soup, asymptotic limit soup or phase diameter, this diameter is bounded by like 1 over k. So if coupling strength is large enough, you can adjust, control this upper bound, the size of diameter. But so it's not, I mean, this is what we can do at the moment. But in the finite dimensional Lohe model, we have an exact estimate. So still, one of my students is working on that direction. In the meantime, Professor He Young-jin is also my classmate in undergraduate. So what we are doing, for example, so special case of one-body potential means you have a common function plus add some constant. This constant may different, may not be the same. So somehow it's congruent, but it's just the height are different. So in that case, if you use this quantity, this L2 inner product, then it turns out this quantity, now you take it, integrate out the space dependence, so it's a function of t. It turns out this quantity satisfies this closed differential equation. Okay? This was quite surprising because you see, this is infinite dimensional dynamics. Okay? If you integrate out the space dependence by taking inner product, then it has a finite dimensional system. Okay. So, if you have a finite dimensional system, then you can use this nonlinear dynamic system idea, machinery there. So, we can, for example, if you decompose Hij, real part, imaginary part, and the real part, imaginary are coupled to each other. Then, for example, let me skip that. And you can talk about the basin of attraction, okay, by using this dynamic system approach. So, for example, the imaginary part equals 0 means it's a real line. If the real part is this, then you can show that this guy is positive invariant set, and also we have a certain complete synchronization even in this case. But of course it's later special because we take a special class of one-body potential. So I think we hope many new story will come out soon. Okay, so you might ask, can quantum synchronization be realizable? In 2012, two physicists, the French physicist Serge Haroche, I don't know in French, but American physicist Wienerland, they got Nobel Prize because of this so-called laser invention of laser spectroscopy, something like that. So this is a quotation from their work. For groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. Okay? Now we are in the stage control each quantum particle. Okay? So quantum network is not just an imaginary thing. It can be real. Although I don't know how to do it, but it can be realizable. But at the moment, I don't care whether it's realizable or not. But I just want to say the best way to predict your future is to create it. Okay? Thank you.